morning. Today we're going to continue on in our bonding unit. We've talked about ionic bonding, ionic bonds, covalent bonds, naming them, forming the compound, or getting the formulas for them. Today we're going to go into dot diagrams, kind of keep progressing on, while including the stuff that we've done before. All right, so up first is your bell ringer. Here it is. What type of bonds are in the following compound? So the first one I'll go over with you. The second one is up to you to figure out. So remember to figure out what type of bond it is. All right, well, first things first, if it has a polyatomic ion on it from table E, then it's going to be ionically bonded. It technically has both bonds in there, but we'll talk about that in the unit. But for now, it's ionically bonded. If it has two elements, so it's a binary compound like these two compounds are, all right, you do the electronegativity difference. All right, so you have to look up the electronegativities of calcium and bromine, and in this case, sulfur and oxygen. You find those on table S. I'm flipping for table S right now because I don't remember the oxidation, the electronegativities. So calcium's electronegativity, when you look it up, calcium's electronegativity is 1. Bromine's electronegativity is, where's bromine? Bromine's 30. Bromine is 3. So 3 minus 1 is 2. So that means it's got a difference of, or 2.0, which means it's an ionic bond, all right, or an ionic compound. Sulfur and oxygen. Sulfur, you look up, electronegativity value is 2.6. Oxygen, the electronegativity value is 3.4. You subtract those two, you get 0.8. So it's less than 2, so it's definitely covalent. And then we can go a little bit more specific. Because it's 0.8, it's greater than 0.4, so it's a polar covalent bond. All right, and that's going to be important as we go on in the year. Okay, so top compound is ionic, bottom compound is polar covalent. Okay, so today we're going to talk about Lewis structures or electron dot structures. This first slide is complete review of the periodic table unit where we did these, and then we'll move on to compounds. So for individual elements or ions, all right, so ionic compounds can be drawn as Lewis structures because they're essentially ions. All right, they're 2 ions, 3 ions, 4 ions. They're in proximity of each other, and because of opposite charges, they are attracted to each other. A term that's new for us right now is a positive ion is a cation. All right, a negative ion is an anion. All right, kind of a way to remember that is cat has a T in it, which looks like a plus sign, which would be a positive ion, and anion's got an N in it, which is negative. All right, which is the beginning of negative. So it's kind of a little trick to remember. Since all of the valence electrons are removed, no valence electrons are shown. So if we start off with sodium, here's a sodium atom. All right, it's sodium with its 1 valence electron. If you look on the periodic table, it's got a +1 oxidation number, so that means it's going to lose that electron. So we're going to write down the bracket charge because it's at a +1, and then it loses the electron. So this is the completed dot diagram for the sodium ion. Okay, it's technically, I know if you look at its electron configuration, it's got 2 in the first energy level and 8 in the second, but we don't drop down energy levels. We just draw it as its original valence shell. So it's going to have no dots around it. All right, and we write the charge up to the upper right. So negative ion or an anion, all right, it's got a full valence shell. So it's got 8 electrons. So these are negative ions. So we'll take chlorine. Chlorine atoms dot diagram normally looks like this with 7 dots around it. You look on your periodic table and it's got a -1 charge is the most likely oxidation number. So that means it's going to add in an electron here. All right. And because it does that, we have to now have, it now has an unequal number of electrons versus protons. So we have to show that it's charged or represent its charge. So we add the brackets and then the -1 there to show that it's got a -1 charge. That should be review minus the term cation and anion. All right, so now we're going to start to put these things. Now, these are rules for elements. Now we're going to put these into compounds. All right, and compounds generally have the same set of rules. Most atoms want 8. All right, but we're going to see that we can get things called double bonds and triple bonds. I don't know if I'm going to get into those today or not. We'll see how far we get. But the individual atom rules do get modified a little bit when they're in compounds to make the compounds quote unquote happy. So here we go. So covalent compounds. So we're going to start off with the elements in the compound. So we're going to deal with water. Water, everybody knows what water is. All right, its formula is H2O. So what I recommend you do is you draw the puzzle pieces. All right, and what I mean by puzzle pieces is in this case, you have one hydrogen, two hydrogens, and then one oxygen. So you draw your hydrogens and your oxygens, and then you're going to draw the individual dot diagrams. Now these are covalently bonded things. All right, if you did the electronegativity difference between hydrogen and oxygen, what's hydrogen's electronegativity is 2.2, oxygen is 3.4, so it's a 1.2 difference, so it's definitely polar covalent. What that tells us is we do not need brackets, we do not need charges. So we do the individual atom dot diagrams first. So hydrogen's got one valence electron, so we put the one on each of the hydrogen atoms. All right, and then we look up oxygen. Oxygen's got 6 valence electrons, so we put those 6 valence electrons incorrectly. All right, not just anywhere. So you put the first 2 on one side, and then they spread out, and they double up a side. So what you end up with is this oxygen with a single electron on 2 neighboring sides. And when we get later on in the unit, we're going to talk about 3-dimensional. I'm going to have to do it 3-dimensionally. Right now, we're just doing it in 2 dimensions. This is a big difference. All right, as we go through. So now what we have to do, we know covalent compounds share electrons. Hydrogen needs 1 more. Oxygen here needs 2 more. So what happens is generally speaking, is the other atoms are going to come into the side that only has 1 electron, generally speaking. So here we're going to add a hydrogen to the left side and a hydrogen to the bottom. So when we put it together. So now we're going to move them together in pairs. So now we get the oxygen here. All right, we're going to add a hydrogen down here. So now hydrogen can claim these 2 electrons right here, even though oxygen's claiming the same 2 electrons. That's called the sharing of electrons. Okay, and then we bring in our other hydrogen over here, and we bring it on the left side. Once again, this hydrogen now, because it's got the 1 electron from itself and the 1 electron from oxygen, all right, they both claim these 2 electrons. So this hydrogen atom is happy. This oxygen, because it's claiming these 2 electrons here and these 2 electrons here, plus these 2 and these 2, it has a total of 8. So it's happy. All right. So water takes on this structure, shall we say. All right. And it looks flat in this world. And we'll see that it's really not when we get into the 3-dimensional stuff. But right now we're just doing 2 dimensions. Okay. So here we go. So I'm going to go old school and write this because writing on the board doesn't record for whatever reason when they change things out. So I'm going to have to write these, which is fine, not a problem. So we're going to deal with a compound between fluorine and magnesium. So we're going to have fluorine and magnesium. Sorry, lefties, my hand covers whatever. All right, so we're going to write a compound, or we're going to do a compound between fluorine and magnesium. All right, and what I want us to draw is the dot diagram, or the Lewis structure. Those names are used interchangeably. So the dot diagram, or the Lewis structure between the compound between fluorine and magnesium. Okay, first things first, you have to get the symbols for these. Okay, so this is where knowing your elements is helpful. But if you look up, fluorine is symboled F. Magnesium is symboled Mg. Okay, the next thing you need is their oxidation numbers. Okay, so if you look up on your periodic table, fluorine's oxidation number is -1. Magnesium's oxidation number is +2. Okay, so we got to get the formula of the compound first, is realistically what we're doing. Now, if you remember before, you have to write the positive ion first. So in our compound, we have to put the magnesium first. All right, and we're going to have to put the fluorine, because it's a negative ion, we have to put that one second. So we just have to be careful with that. So down here, I'm going to write magnesium. I'm going to actually change these colors so that they have different colors. So magnesium is going to have its +2. And then fluorine is going to have its -1. Okay, so now we crisscross jump. Okay, and you get the formula of this compound as being I'm going to go back to blue. No, do I want to go back to blue? We'll write it like this. We'll go Mg, and then the subscript's going to be a 1, so I'm not going to write the 1. All right, I have F, which I need to write in green, all right, which is going to have a subscript of 2. So the formula of our compound is MgF2. Before we can go any farther, we have to figure out its electronegativity difference. So over here on the side, I'm just going to write down En difference, because you have to do this every time. All right, and you're going to look up the electronegativity differences of magnesium and fluorine. All right, fluorine I can tell you is 4.0. All right, it's the highest electronegativity value on the periodic table. Magnesium's electronegativity difference, or electronegativity value, is 1.3. So when we subtract these two, we get 0.7, all right, 2.7. So 2.7 means this is ionic. Okay, so now we've got an ionic compound. So that means we're going to have brackets and charges when we're all said and done. Okay, so first things first is we're going to do our puzzle pieces. So our puzzle pieces, so we've got 1 magnesium atom and 2 fluorines. So I've got a magnesium. All right, I look up on the periodic table. Magnesium's valence electrons are 2. So I'm going to put magnesium's 2 electrons up here. And then we've got fluorine. We got 2 fluorines. Fluorine. All right, and each fluorine has 7 valence electrons. So I go 1, 2, 3, 4, 5, 6, 7. All right, and I'm going to do the same thing for the other fluorine. 1, 2, 3, 4, 5. Notice what it looks like with 5. All right, you do 2 on the same side, then spread out the other 3, and then 6, and then 7. Okay, so now we have all of our puzzle pieces. Now we have to put them together so they're quote unquote happy. Now, because they're ionic, all right, that means they're going to transfer electrons. All right, these things are going to transfer electrons. So that means one thing's going to lose electrons, one thing's going to gain electrons. Looking at our electronegativity values, fluorine's got a much higher electronegativity value than magnesium. So what's ultimately going to happen is that magnesium is going to lose these electrons to the fluorines. Okay? So here we go. And this will come with practice. Generally speaking, the single element is going to be your central atom. So I'm going to write Mg here. All right, it does not matter what side you put these electrons on. You can put them on any of these 2 sides because when they're in compounds, they're going to split up. So what I'm going to do just to make life easier to write this is I'm going to put an electron here, an electron here. I'm just splitting them over the 2 magnesiums. All right, and now what I do is I bring in my F over here with its 7 valence electrons. And I'm going to put that one right there. And then I'm going to bring in my F over here with its 7 valence electrons. All right, because it's ionic, I'm not done yet. I need brackets and charges. I have to put brackets around the elements that take the electrons. And I'm doing this in different color. You can do them all in the same color, but just try to make it stand out. So here, because fluorine's got a higher electronegativity, it's taking this electron from magnesium. So I have to put the bracket to show that that electron comes into the fluorine. All right, then I put the other bracket here. I'm gonna do the same thing on this side. And now all we have to do is to write our charges to finish out this particle. All right, so magnesium started off with 2 electrons. It lost 2 electrons. So now magnesium's charge is +2. Which should make sense to what we started with up here. All right, let's see how we get back to that original charge. All right, fluorine, this fluorine atom, because it picked up 1 electron, is a -1. Notice what we started off with fluorine up here is -1, -1. We're good there. And this fluorine atom is also a -1 because it picked up 1 electron. If you've properly made a compound, the sum of all these charges should add up to equal 0. All right. Oh, one thing I did forget to write down up here is the name of the compound. Right, I'm just writing it in yellow because I want to see what this marker looks like because my black marker is dying. The name of the compound, because you got magnesium and fluorine, the name of this compound is magnesium. Yeah, that shows up, all right. Fluoride. All right, because remember, ionic compounds don't use prefixes. So we're putting lots of things together in here. Okay, so that's the first one. And we're going to do quite a few. I don't want to say quite a few, probably 5 or 6, depending on time here. Okay, so that's the first compound that we've done. All right, next one. Once again, we're going to do a dot diagram. Oops, probably shouldn't write on another piece of paper. Let's see if I can, that looks better. Okay, so I'm just going to put the screen one under here so it doesn't screw my board. All right, so once again, we want a dot diagram for a compound between, or the compound's name, I'm going to give you the name this time, is sodium hydroxide. So sodium hydroxide. Okay, so you got to get the formula of this, so I would probably pause this so you can ask you this because you should be able to do this right now. So sodium, hopefully you know, sodium is Na. Hydroxide you would look up on table E. For those people that forget what table E is, table E is on page 2 of your reference tables. All right, I have my reference tables just like you guys do. All right, hydroxide, if you look here, hydroxide is right here, is OH with a -1. So OH. All right, since we have to figure out the formula, we're going to need the charge. So I'm going to put anything off the table E, it's just easy to put parentheses around it. Put a -1 there. Sodium off your periodic table is +1. Okay, so now we crisscross jump, and we get the formula of the compound as NaOH. Now, the nice thing about this one, because it has a polyatomic ion in it, we don't have to do the electronegativity difference. It's got 3 elements, so you can't do an electronegativity difference if it's got more than 2 elements. So this one is going to be an ionic compound. All right, technically speaking, the bond in between the O and the H is covalent, and then the bond between the OH particle and the Na is ionic, so it has all kinds of bonds in there, but we're going to draw the diagram as an ionic compound. Okay? All right, so first things first, like we did before, is we're going to get the puzzle pieces. All right, our puzzle pieces in this case, those colors now. All right, sodium, and we've got hydroxide. All right, hydroxide, actually this. So we're gonna have O and H. Sorry, I forgot. We're gonna split out into its polyatomic ion. All right, so I didn't do different colors. Blah 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 blah. So we're gonna do. Let's see. I think I can overwrite this in blue. Blue. All right. So hydrogen, it's got 1 dot because it's got 1 valence electron. Oxygen has 6, 2, 3, 4, 5, 6. All right, and then sodium over here has 1. Okay. So what happens here is the hydrogen is going to bond with the oxygen. All right, so you're going to end up with O here with its 6. I'm going to do H in green. All right, and it looks like that. Then you still have your sodium with its 1, doing it like this. Okay, so you have what's going to happen here. So now for this thing to form a compound, there's got to be a transfer of electrons because you've got sodium with 1, you've got oxygen in this case with 7. So what happens is we actually get a transfer of electrons from the sodium to the hydroxide particle. So let's see here. If we go sodium with its dot, we're going to go oxygen with its 6. And then we've got hydrogen with its 1. Okay, so we've got the particle. So now we have to show a transfer of electrons because right now oxygen looks good because it's got 8. Hydrogen we can technically say is good because it's got 2 because it only has the first energy level. It looks like sodium right now has 2. Sodium's not good with 2. All right, either needs 0 or 8. But because it's an ionic compound, because it loses its dot over to here. All right, what ends up happening is we put a bracket around, just like we had parentheses in the beginning, we put a bracket around this, all right, to show that this hydroxide takes the electron from sodium and it picks up that -1 charge. Sodium, because it lost the 1 electron, is +1. All right, and if you look, that the charges are what we started with up at the top. Okay, and you end up with your final particle looking like that. It's ionically bonded, so you need the dot, you need the brackets, you need the charges. All right, your charges will add up. Everything's dots will make sense, and having 0 for the sodium in this case, 8 for the oxygen, and 2 for the hydrogen, because hydrogen only has first energy level. All right, that's a harder one. It's a polyatomic ion, but we do have to become familiar with them. All right, let's do another one. All right, I'm trying to show you all kinds of different scenarios here. All right, the practice for you comes from what you guys do. I'm just going to see if I have a different black Sharpie, because that Sharpie's died. It does not look like I have one. All right, that's fine. Okay, we'll just go with other colors. So now we're going to do CO2. CO2. All right, so we're going to do the dot diagram for this. All right, first things first is we've got to figure out its name and electronegativity. Well, we'll do electronegativity difference because that'll help us figure out its name. Electronegativity difference, so over to the side or whatever, you've got carbon. You've got oxygen. All right, carbon. I know oxygen's 3.4. I don't know what carbon is. Carbon is 2.6. 2.6, 3.4. All right, you do the difference between those, you get 0.8. All right, because it's 0.8, it's said to have polar covalent bonds. So all this work has to be done. I highly recommend writing it down because it helps train your brain for the process. So now we got to name this as a covalent compound. Remember covalent compounds? Normally, if it was ionic, we would call it carbon dioxide. All right, but because it's a covalent, we have to use prefixes for the number of atoms. So you've got 1 carbon, which because it's the first one, we don't use the prefix mono. So we just write carbon. And then we have to write the number of oxygens we have. We have 2 oxygens. The prefix for 2 is di. So carbon dioxide, which I think many people are familiar of for carbon dioxide. Okay, I will tell you, this dot diagram is not a fun one in any way, shape, or form, because it introduces something called a double covalent bond, where they share 2 electrons instead of, or 2 pairs of electrons, I should say. All right, so here we'll draw our puzzle pieces. We've got carbon. It's got 4. So carbon's 4 looks like that. Oxygen has 6. So there's 1 oxygen atom. Here's our second oxygen atom. Okay, so now we have to put these together. Now it's a covalent bond, so it's not going to transfer electrons. We're actually going to share them. So we have to ultimately end up with carbon with 8 electrons around it, oxygen with 8, and oxygen with 8. So like I said before, because you have like 1 atom and 2, you're going to have a central atom, which is going to be carbon in this case. All right, I'm going to tell you more often than not, carbon is going to split out its electrons like this, 1 on each side. So I'm just going to start that off right now. Okay, we're going to put an oxygen on whatever 2 sides you want. It really doesn't matter. I'm going to do it on the left and the right just because of space. So we have our oxygen here with 1, 2, 3, 4, 5, 6 electrons there. Then we have our oxygen over here with 1, 2, 3, 4, 5, and I'm going to put the 6th one here. Okay. So now we look at this. If we look at the carbon, carbon's got 1, 2, 3, 4, 5, 6. It started off with 4, it's got 6, so it's closer, but it's not done yet. Oxygen has 1, 2, 3, 4, 5, 6, 7. And then this right oxygen has 1, 2, 3, 4, 5, 6, 7. So it's close. So oxygen needs 1 more. So what we can do here, because oxygen needs 1 more, we can take that electron for carbon there and put it over there, and that electron for carbon there and put it over there. So now if we count up the oxygens, you got 1, 2, 3, 4, 5, 6, 7, 8. Oxygen's good. 1, 2, 3, 4, 5, 6, 7, 8 carbons, or that oxygen is good. We look at the carbon in the middle now. All we did was move the electrons. So 1, 2, 3, 4, 5, 6. We still only have 6. So what we have to do with the oxygen to make carbon happy is take this dot and move it up on both sides so that they can kind of claim it. So what we end up with is we end up with a carbon atom in here. If we look where what we did is we have 2 dots of carbon here and 2 on this side, because we took the one on the top and brought it down. We put the one on the bottom and brought it up there. All right. Now we have our oxygen atom. All right, with it's 1, 2, 3, 4 like we have here. And then we're going to put the 2 in here because we brought 1 up there and we already had 1 right there. So it ends up like that. We're going to do the same thing on the left side. 1, 2, 3, 4, 5, 6. All right, and what you end up getting here is the carbon and oxygen sharing 2 pairs of electrons. So it's sharing this pair of electrons and this pair of electrons. And then same thing's happening over here on the right side. So what happens is this carbon got 1, 2, 3, 4 here, 5, 6, 7, 8 there. So if you just draw like your Venn diagrams like you did back in the day for whatever class, this carbon now has 8. And if I do it in a different color over here, this oxygen has 8, and this oxygen over here has 8. Now I'm going to draw the diagram again because we don't draw the circles around these. So I just want to make sure that we're good to go with this. So our final diagram for carbon dioxide. So you got carbon with its 4. You've got oxygen with its 6. Oxygen with its 6. So there's our final dot diagram. If you want to in here, you can connect these and make a line. All right, but it doesn't matter whether you leave it as dots or a line. They're interpreted the same way. Okay, so that's a really hard one. Okay. And I'm kind of going through these, just showing you the different things that can happen. Okay, the next one we're going to do is a compound between strontium and bromine. So we're going to do strontium. Yeah, we'll do with this. A compound between strontium and bromine. So the beauty for you is you should pause the video and try to do this all on your own, and then I'm just going to continue going on with it. All right, first thing we got to do here is electronegativity difference. All right, so electronegativity difference. So you've got strontium. Oops, sorry, I wrote a small s. Strontium and bromine. So strontium is element number, what is it up there? 38. So you go down to 38 on table S. Strontium has got a 1.0 electronegativity value. Bromine is 35. So you go to 35 for bromine. Bromine's got a 3.0. So 1.0 minus 3.0 is a 2.0 electronegativity difference, which means this thing is ionic. Okay? All right, so now you need your symbols. So strontium, hopefully you know strontium is SR. Bromine is BR. Looking at your periodic table, you need to get their oxidation numbers. So strontium is a group 2 element, so it's going to be a +2 charge. And then bromine is a 17, which is going to be -1. Crisscross jump jump. All right. Now we're good. We don't have to flip around the elements because the positive one is first and the negative one second. So we're good with that. All right. And then we crisscross jump jump, and you end up with this formula of the compound here as SR1 BR2. So SRBR2. Okay. So now we need to do our puzzle pieces. So we have 1 strontium. Strontium, because it's a group 2 element, it has 2 valence electrons. All right, we've got bromine. We have 2 of them. 1, 2, 3, 4, 5, 6, 7. There's 1 of them. And here's our other one. 1, 2, 3, 4, 5, 6, 7. There's our second one. Okay, so now we have to find a way to put these together. All right, it is ionic, which means they're transferring electrons, so we're going to have brackets and charges. All right, we have to show somehow that one atom is going to lose electrons and other atoms are going to gain electrons. All right, because we have 2 and 1, we're going to have a central atom for strontium. Usually when you have a central atom, you're going to split the electrons on opposite sides. So I'm just splitting the electrons like that. All right, I'm going to put a bromine on the left, or on the right mirror. I'm sorry. 1, 2, 3, 4, 5, 6, 7. There's a bromine there. And then I'm going to put a bromine on the left here. So 1, 2, 3, 4, 5, 6, 7. I'm not going to put it there. Now notice, one way I drew it like this, where they're side by side, and one way they're top to bottom. It doesn't matter. Either one works. Okay, but because it's ionic, we have to show a transfer of electrons. We know because bromine's electronegativity value is the greater one, so bromine's going to take the electrons. So I'm going to draw brackets around the bromine with its dots that it took. I'm going to do the same thing on both sides. All right, now here, bromine picked up an electron. So it's going to be -1 on this side. It's going to be -1 on the left side. The same thing as it picked up one electron. Strontium lost the 2 blue electrons, so it's a +2 charge. Notice it's similar to the charges that we started with. All right, if we add up all these charges here in a compound, it's 0. That's kind of a clue that we are done with it. Okay? All right, so that's strontium bromide. I'm going to do one more, and this is an old school compound. Old school compound, I'm going to give you the formula of the compound. The formula of the compound is NH3. All right. Old school name this is called ammonia. And I tell you this because you need to know this. All right. NH3 is ammonia. And this is also one of the classic compounds that they're going to have you draw for dot diagrams. I don't know why. That's its common name. Its scientific name is nitrogen trihydride. All right. Because it has the prefixes in it, that should clue you in that this is a covalent compound. Okay, so we don't have to do electronegativity differences because I'm telling you its name. Okay, but we call this ammonia. I'm never going to call this nitrogen trihydride. It's like calling water. All right, technically water is dihydrogen monoxide. But we call it water. It's just, it was named that way before the naming rules came out. Okay, so we're going to do this one. So we have 2 puzzle pieces here. We have we have nitrogen and we have hydrogen. So we have nitrogen and we have 3 hydrogens. All right, nitrogen has 5 valence electrons. If you look on the periodic table. All right, hydrogen has 1. All right, we know it's covalent because it used prefixes in the name. We could do the electronegativity difference as well, but we don't have to because we know the name. All right, so now the nice thing, because it's covalent, we know they're sharing electrons, and because there's 3 hydrogens, the nitrogen's kind of got 3 spots for it to come in. So we draw our nitrogen as our central atom because it's the lone one. 1, 2, 3, 4, 5. And then we're going to bring in a hydrogen on the right, a hydrogen on the bottom, and a hydrogen on the left. And you end up with that as your dot diagram. Now, you don't need brackets. It's covalent. Nitrogen is happy with 8. Hydrogen is happy with 2. And we are good to go. All right. That wraps up our dot diagram stuff. You guys are going to continue to practice with this stuff. It's the only way you're going to get it. And then we'll talk later. See you in class tomorrow or Friday.